Hi guys, today I would like to talk about a different topic which is closely related to the integral, but it's kind of the uh, other flip of the coin, basic side of the coin. So today we'll talk about derivatives, and I will start with some very simple introduction, and then I will try to get to the point where I give a more standard definition of it. But let's start with the basic notations and ideas. So think about a quantity of any kind that you like. It could be expressed in any unit of measure that you want, kilograms, meters, energy, power, whatever. Think about a quantity, and let's call this quantity F. Okay. Now, since this quantity um, can be thought of related to something that you can add and subtract, for example, we can safely think about uh, two different quantities of the same quantity, F2 and F1, and do the difference of the two. Oops, this is should be 1, because otherwise it's 0. And let's put, oops, this is another color. Oh, sorry, and this is 1. Okay, this is a mess. Okay, this is the correct F1. And let's be graphic about it. So this difference of these two quantity, we don't know what 1 and 2 stands for, but they are just two labels to say that the quantity varied somehow, and let's call it delta, big delta F. Okay, this is a variation of a quantity. Okay, uh, and now we can do this with F, and then we can think about another quantity. Let's call it T in this case. Um, I'm thinking about time at the moment because it's easy to fix the your ideas on a quantity that varies in time. For example, there are plenty of examples of quantities that varies in time. It can be velocity, it can be space, it can be, I don't know, your energy power consumption in your flat, or any other uh, electrical device, the speed of your broadband. I mean, think about any function that varies in time, and that could be a good physical example. But let's keep it abstract for the moment, and not fixate about time. I will use t anyway. So we can do the same thing. We can say delta t is equal to, let's pick the same label, not to complicate our lives, t2 and t1. This means that we are thinking about the variation of two quantities that don't have to be the same, but let's say with some connection between the two. Here the connection is they have the same label, for example, T1 and T2. Now to be precise, and the connection that I want to do, it's a bit stronger than that. So usually a derivative is taken um, on quantity f that actually depends on the other quantity t in this case. Um, so it may be not the most abstract way to look at it, but let's just fix this example. And there is we already seen that in other slides on the integral, the definition of function, and in this case it's perfect to think about this relation between these two quantities as a function. So we are safely we're comfortable in saying that f is a function of t in this case, and we write it like this. This is a nice way to say pick any t that you want, put it inside f, and then f will spit out another number. Let's call it y. Usually it's referred as y. And this rule that can be as complex and as easy as we like. I mean, we don't need to be fancy now, but let's usually draw it in the usual way. On the Cartesian axis, we have t in this case on the bottom axis, and y in the vertical axis. And let's start with the boring thing, the easy example. The usual, I will start from 0. Let's not bother with the negative numbers for the moment. In 9, let's just consider positive numbers. That's enough to understand the concept. And this is a straight line. I'm not drawing too well, but it's the usual starting point, which is x, sorry, not x, I call it t, let's stick with t, like t equals to y, okay? And just to refresh ourselves, this idea of function in the graph, how do you read this association with this rule that we just define up here? We say that if we pick any time t on 0, for example t on 1, let's say, this number here could be any number that you have in mind, will be exactly the same in y. F dt on y, dt on 1 is y1, and they will be the same number. So if this is 1, this will be 1, this is pi, this will be pi, square root of 2, square root of 2, and so on, whatever, it's the same number. Okay, so this means that there is a precise relation between these two numbers. Okay, now where do we want to go with this derivative? I didn't say what the derivative is yet, but and I will not do it soon. I will just go through another step before, which is the following. So we have this rule in mind, which I will keep highlighted up here with maybe this color, just to remind that this is important for us. And then we can start to define something. So these two quantities, once we've put on a graph and we talk about numbers, we can always take the four easy operation on number, which are summation, multiplication, and division and subtractions. So we are already using the subtractions here, and I'm just going to use the division to do my step further. So we know what a division of two numbers is, so we know how to take the division, the fraction of two numbers. Let's do it. So we do delta f divided by delta t. Okay, this is just a ratio of two numbers. Hopefully we picked these two numbers t2 and t1 such that they are not the same, and this is crucial to define this number correctly. Otherwise we would have something divided by 0, which usually is infinite, and we don't want to go there at the moment. But let's pick, we are dealing with this t equals y, and if we pick any number on the right of our Cartesian axis t, we should be with this function here, we should be fine as long as t1 and t2 are different. So let's write this more graphically, and let's say that this is f of 2 minus f of t1 divided by t2 minus t1. I'm just expressing what we already know. So easy steps, we can do differences of things that are the same. We can do fractions of number. Now the dimension can be different, but let's not think about the dimension like the physical dimension, like kilograms over time or meter over time. At the moment, just look about the number, and then we can deal with the physical dimension later on. So this is a kind of ratio that wants to be a derivative. But before going there, I want to show you what you can do with this ratio. Okay, let's call this ratio for the moment A. Okay, we pick this color blue and we call it A. Why? Because I like this color, I like the letter A, and I don't like to write too many letters. So let's stick with A. And then with this in mind, once we've got this number, what we can do is we can retrieve any point in this graph by knowing this number only, and the variation on the bottom axis. So to be more specific, let's cancel this. Remember of A, we put it A up here, A up here. A is an oops, I don't want this color here. I want a lighter blue, which is nicer. Light blue A, and this is our, let's say, compact way of writing delta F of delta T. So I'm jumping ahead here because I know already that this in this particular case where t equals to y in any point, actually this ratio is a fixed number. I will show you why. So it's good that we can call it with a specific name, which doesn't change wherever you pick this variation. So for the moment it's just a number. But let's see what we can do with this number. So as I said, we can reconstruct any point. How do we do it? So we know that the difference of 2 points, f of t2 in this case, minus f of t1 can be written as a times t2 minus t1. It looks like I'm juggling with the numbers, but if you look carefully, I didn't do anything wrong or crazy here. I just pick this difference, which is delta t, and since it's not zero, I can do that, and I can bring it back and forth between the two sides of the equation. So if you think about it, you can dot the line here of the fraction. You can go up and down as you like, because this is not zero. So nothing fancy here. I'm just showing you that if we know this particular number for the given function a, which is the derivative, which will be the derivative in this case, we can reconstruct any point. So any point of the function we want just by giving the value of the increment in the t coordinate in this case, so the quantity that is dependent on it. And the step is easy, so we can I mean that's the basic idea, right? So we can see that f of t2, okay, we need to know a little bit more. We need to know at least the value of the function in f in t0, but in this case it's easy because we can start with t1 equals 0, and since this line starts from 0, we know we can